Hello ladies and gentlemen, today we will be looking at another sampling distribution. This time, instead of sampling proportions, we will be sampling the means of simple random samples. So we should be able to find the mean and standard deviation. We should be able to calculate probabilities when we're approximately normal. We should be able to talk about how the sampling distribution of the means is related to the shape of the population distribution, and we should be able to apply this thing called the central limit theorem to help us find some probabilities. Alright, here we go. Sample means. So in the previous section we were talking about sample proportions. These most often are used when we're dealing in categorical variables. But when we're dealing with quantitative variables, we look at mean, median, standard deviation. Most of the time we're looking at calculating the mean as a statistic. So here we have two visuals. Consider the mean household earning for sample size 100. Compare the population distribution with the left with the sampling distribution on the right. What do you notice about the shape, center, and spread of each? So this is our population distribution. This represents our entire population. This represents a bunch of samples of size 100. So notice that the mean is still roughly in the same position. Here's our population mean. The mean of these samples looks to be about right here. The center, so that's our center. The shape, the population looks to be skewed right. However, our sampling distribution, the shape appears to be fairly normal. The spread of the population compared to the spread of our sample is significantly larger. Our sampling distribution has a much smaller spread than does our population distribution on the left. So, if we're choosing many SRSs from a population, the sampling distribution of the mean will be centered at the population mean and will be less spread out than the population distribution, and that is fact, ladies and gentlemen. X bar is the mean of an SRS size n. That population has a mean mu and standard deviation sigma. Then the mean of our sampling distribution, when we're sampling a bunch of x bars, is mu sub x bar, and that will always equal mu. The standard deviation of our sampling distribution of means, so again we're sampling a whole bunch of means. We're collecting 100 items, finding the mean. Collecting another 100 items, finding the mean, and then we're taking the standard deviation of all those means. That's why this is sigma sub x bar, the standard deviation of the sample means. That can be found by taking our population standard deviation, dividing by the square root of n. And that is as long as this 10% condition is satisfied, meaning our sample size needs to be less than or equal to 1/10 of our population. If that's true, then we can find our standard deviation this way. And these facts, this mean and standard deviation, it's true no matter what shape our population distribution has. Our population does not have to be normally distributed. It could be skewed, it could be uniform, it could be some random distribution, but these facts, these mean and standard deviation relationships will always exist. So visually, here's what's happening. We have this population. We're collecting a whole bunch of simple random samples of size n, and collecting all of these means. If we do a dot plot or a histogram and look at how all of these means fall, it should be approximately normal, with the mean being the same as the population's mean, and our standard deviation, our measure of spread, is sigma over square root n. So,
it's 3 o'clock.
We've described the mean and standard deviation, but we haven't talked about shape yet. The shape of our sampling distribution depends on the shape of the population's distribution here. with our proportions, it didn't matter what shape the original population was. Our proportions always ended up coming out normal. If we have our means that we're sampling, the shape of the original population matters. It's very important. There is one special relationship between population and sample. If the population distribution is normal, the sampling distribution will be also, no matter what size the sample is. It doesn't matter if we're taking samples of 2 and finding the mean. Our sampling distribution will be normal. And let's take a look and see what that looks like visually. Here's a website. It's from Rice University. And let's bring up a normal distribution. I'm going to collect means sample size of 2 and sample size of 16. And I'm going to collect 100,000 of these means real quick. There we go. So it doesn't matter that I only selected sample sizes 2, sample size of 16. Our sampling distribution is approximately normal because we're starting from one of these normal distributions. We'll look at some of these others in just a second, but let's go back to our note-taking here. Suppose that here's a formal definition for us. Suppose that a population is normally distributed with mu and sigma, then the sampling distribution of x bar will have a normal distribution with mean mu and standard deviation sigma over square root n as long as the 10% condition is met. And let's look at an example here. We've looked at the heights of people repeatedly throughout this course, and we've always looked at the heights as being normally distributed. So the height of young women follows a normal distribution with a mean of 64.5 inches and a standard deviation of 2.5 inches. Find the probability that a randomly selected young woman is taller than 66.5 inches. This is old. This is not anything new. Our x is going to be the random variable for height of a randomly selected young woman. X will have the distribution of normally distributed 64.5, 2.5, mean standard deviation. We can find our z-score. We can use table A, or we can use our graphing calculator to figure out that our percent is 21.19%, that a randomly selected young woman is taller than 66.5 inches. So that's old. Great. But what about this new stuff? What about this sampling distribution thing? Find the probability that the mean height of a simple random sample of 10 young women exceeds 66.5. So now we're not talking about the height of one randomly selected woman. Now we're talking about the average height, the mean height of a simple random sample. So here, our mean is still 64.5, but we're now talking about the standard deviation of the means. Standard deviation of our sample means will be 2.5 over square root 10, or 0.79. So because our original population was normal, our sampling distribution will be normal, but note the change in the standard deviation. Again, z-score, table A, or graphing calculator, we get 0.0057. So it's very unlikely that we would choose a simple random sample of 10 women and have their average height exceed 66.5 inches. So visually, here's what just happened. The population distribution is the purplish normal curve here. Mean standard deviation is bigger. Here's the 66.5. Note how our sampling distribution changed. Our standard deviation went down significantly, and the percent under the curve has shrunk significantly also.